Okay, good morning everyone. I hope you have been enjoying a long weekend. Okay, but do find some time to rest and do some work. Okay, for this video, we'll be going through, actually, this is the 2024 WA2. Okay, so the topics tested are light, static electricity, and current of electricity. Okay, for practice on DC circuit, please look at my previous video. You should have been given the 2023 WA2. Okay, I'll be pasting all the answers here so that I don't waste any time in the video. Okay, let's start. Okay, question 1 for MCQ. Diagram shows a ray of light from one point on a lamp striking a plane mirror. So if it's a plane mirror, you will know that it is actually undergoing reflection. Okay, so for reflection, the image will be at P. Okay, so because the lamp is now the object, so we draw a normal. Okay, so the this is where the image will be. Take note that it must be equal distance. Okay, so and because there's nothing behind the mirror really, so it is going to be virtual. Meaning of virtual is that cannot be projected on a screen. Okay, the image cannot be projected on a screen. So answer is D. Okay, negatively charged metal sphere X is moved close to an uncharged metal sphere Y, and the spheres do not touch. That means the electrons cannot actually move into Y. So if it's brought near, then the electrons in Y, take note, electrons in Y will be repelled to the right hand side, leaving behind the protons on the left hand side. You cannot say that the protons are being attracted to the electrons in X. You can't, right? Because protons cannot move. So on the left hand side, we have more P than E. That's why it is net positive charge. On Y, we have more E than P, right? Because of the repulsion. So as light charges repel, so we will have net negative charge. Okay, and then the story tells us that it is Earth by touching it with a finger. So once I earth it, right, it's connected to Earth, all these excess electrons will actually move down into Earth. Okay, so therefore, after it's Earth, it will look something like that. Okay, where did all the electrons go to? They actually went down to the Earth. The finger is then removed, so I will then draw the next diagram. If it's removed, then it will still look like that. Okay, now there's no more earthing, no more earthing. Okay, but why is it that the why is that there's still a net positive charge? Because X is still around. So after that, X is moved away. That means it's no longer under the influence. So now my Y, the whole object becomes net positive charge. Net positive, right? And the electrons within Y will redistribute themselves. The protons cannot move, right? So actually there are still electrons inside. There are still electron and protons pair. The electrons will redistribute themselves, and so answer will be B. Okay, electric field around a positive charge, it will be B. Okay, so why is the direction like that? It's showing the direction of a direction of force acting on a small positive test charge. Okay, so imagine I have an object that is small but it is positively charged. I put it near this positive charge in this question. The force that is acting on this small positive test charge will be in this way. If I put it here, it will be in this way, right? Because of light charges repelling. Okay, so answer is B. Okay, question 4. A charge of 60 coulombs passes through a resistor in 120 seconds. So this is the Q and this is T. Okay, second statement, in 1 second, the energy transferred to the resistor is 5 joules. So this is my W, this is my T, right? So for the first statement, if I have Q and I have T, I can actually calculate my I to be 60 over 120 equals to 0.50 ampere. That means I will have 0.50 ampere passing through the resistor. Then they tell me that in 1 second, we will transfer this energy to the resistor of 5 joules. 5 joules of energy is being transferred to the resistor. They want us to calculate the potential difference across the resistor. Now, potential difference is V. We know this formula, V equals to W over Q. We choose this formula because there's W, there's V, and we actually have Q. Okay, but what is the Q? Remember, if I am going to use this 5J, it is for 1 second. So I cannot be using this 120 seconds. So let me do this again. V equals to W over Q. Q, I can actually make it into IT. So I'm asking for V, I don't know. W, I know, which is 5 joules. I know is 0.5. And for the T, I actually need to use 1 second now. I cannot use the 120 seconds. Because if you read the question, in 1 second, energy transferred to the resistor is 5 joules. So in order to use 5 joules, I need to use the time of 1 second. But the current is the same lah, 0.5 and then 1 second. So I'll get 10 volts. Okay, so answer is C. Okay, a large current flows through the filament in an electric lamp. So filament in electric lamp is non-ohmic, right? Non-ohmic. So that means the resistance will change based on the physical conditions such as temperature. So when the lamp is just switched on, okay, it's cold, right? It's not as hot. So the current is large, they are saying, because when it's cold, when the filament lamp is cold, the resistance is low. Okay, and because V equals to IR, my V from the mains is constant, my R is low, and therefore my current will be high. So answer is A. Okay, let's go to section B. A ray box is positioned below the surface as shown in figure 6.1. 3 light rays from the ray box hit the liquid surface at different angle as shown. Refractive index is 1.47. Okay, so this is N liquid. Okay, it's 1.47. Okay, the answers are shown, but just maybe listen to my explanation if you did not get your answer correct. So they want us to explain what is meant by refractive index of the liquid is 1.47. Okay, so the answer is here. Speed of light in vacuum is 1.47 times that of the speed of light in the liquid. Okay, I'm not really used to this. The one that I teach is the ratio of the speed of light in vacuum to the speed of light in the liquid is 1.47. So actually, this is the formula. N equals to C over V. There's this formula that relates the refractive index of the liquid to the ratio of the speed. Now, just take note, C is actually speed of light in vacuum. Okay, speed of light in vacuum. Although we use V, this is the speed of light in medium. So please don't mix up. Okay, although V, vacuum starts with V, but we use C to represent the speed of light in vacuum. So V will be a speed of light in medium. Okay, and one thing to take note that the minimum value of N of any refractive index is 1. Minimum value of refractive index is 1, which actually belongs to vacuum, because vacuum has nothing, right? So the speed of light is the fastest in vacuum. So later on, if let's say you do your calculation and you get like maybe N to be less than 1, that means your answer is incorrect. Okay, take note. I'm going to erase this to get more space. Okay, part B, they want us to calculate the critical angle for the liquid. Okay, so they use this formula sine theta equals to 1 over N. Okay, but I will stick to my N1 sine theta 1 equals to N2 sine theta 2. By the way, you also need to know the definition for critical angle. And if you know the definition for critical angle, you understand what it means. It means that when the light ray is traveling from denser to less dense, the critical angle is the angle of incidence, okay, in the denser medium, for which the angle of refraction in the less dense medium is 90 degrees. Okay, so this is the formula that I use. It relates the it shows the relationship between the refractive index and the angle in one of the medium to be equals to the refractive index multiplied by the angle in another medium. Okay, so how do I use this formula? I would need to choose air or liquid to be medium 1. Okay, maybe I choose air to be medium 1, liquid to be medium 2. So I know the refractive index of air, it is 1. Okay, sine. Now, take note of this. Critical angle is when the angle of incidence in the denser medium. In this case, the liquid is denser, the air is less dense. So the angle of incidence in the denser medium resulted in angle of refraction in the less dense medium to be 90. Now, the less dense medium that we are talking about here in this question is air. So I know the critical angle will result in angle of refraction in air in the less dense medium to be 90 degrees. So N2 is the refractive index of the liquid, which is 1.47. Then sine, the angle of incidence in the denser medium is the critical angle. So I call it sine C lah. Okay. So if I do my manipulation, sine C is actually 1 times sine 90. Sine 90 is actually 1. So it is equals to 1.47. So actually you have this formula over here. They are the same. Just that for my class, I teach them the M1 sine theta 1 because if you understand it, you don't have to memorize one more formula which tells you the which can help you to find the critical angle. But if you still want to memorize 2 formulas, it's fine. Okay, so with that, I should get sine critical angle to be 42.9 degrees. Okay, take note to put down the units. Now on figure 6.1, complete the path of the 3 light rays after meeting the liquid surface XY. Label all the angles clearly. Now, whenever you see that the light is traveling from denser to less dense, there is a chance of TIR. There's a chance of TIR. Okay, so when will we need to know is TIR? The first condition is that the light must be traveling from denser to less dense. Look at the diagram, the light is actually traveling from denser to less dense. So that means there is a possibility of TIR. To confirm that, your angle of incidence in the denser medium must be greater than critical angle of the denser medium. Now, this critical angle is actually a property of the liquid. So we have calculated that for this liquid, with a refractive index of 1.47, its critical angle is 42.9. However, the angle of incidence in the liquid can vary, right? It depends on how the light is reaching the surface. So if it happens that one of the light ray, it has one of the incident ray causes an angle of incidence to be greater than this critical angle, which is 42.9, then there will be TIR, right? If the first case, the first condition is met, which is the light is traveling from denser to less dense. So now we are presented with 3 light rays. Okay, so the trick to this question is they give us all these angles. These are tricks, right? Because these are not angle of incidence or angle of refraction. These are just angles that the ray makes with the surface. So you really need to draw your normal. Okay, so once you draw your normal, you find that this angle is actually 50 degrees. Okay, this light ray, let's say we call it light ray A, we call it light ray B, and light ray C. Light ray A actually has an angle of incidence of 50 degrees. And your critical angle is 42.9. That means this angle greater than critical angle. Therefore, there will be TIR, total internal reflection. That means this angle will also be 50 degrees. The light ray will not emerge from the denser medium into the less dense medium for light ray A. For light ray B, what is this angle? So you see they put a 90 degrees here. So again, this is a trick. Okay, if you don't draw your normal, you will be tricked by this. The light ray is actually parallel to the normal, which means the angle between them is 0 degrees. Therefore, it will go out unbent. Okay, there's no refraction. Then this 53 degrees, some of you may say, oh, 53 degrees, then it exceeds the critical angle. But again, this is a trick. The angle here is 37 degrees. So if it's 37 degrees, then it is, for light ray C, it is lesser than critical angle. Therefore, there will be refraction. So you actually have to calculate what is this angle, right, using the formula. So you should be getting 62.2 degrees Celsius. Okay? So you have to actually do your working again. So if you want to do, I can quickly do my sine n1 sine theta 1 equals to n2 sine theta 2. My medium one is air. Sine theta 1 is unknown. N2 is 1.47. Sine, how much is that? 37. Okay, so this is how I use this formula. Then you find your sine theta 1. Okay, so this one actually eliminates the idea of knowing is it n equals to sine I over sine r. I know where this comes from when it's traveling from less dense to denser. Okay, but if it's from denser to less dense, then you have to do this. Okay, so maybe a little bit complicated if you, or maybe you forgot which one is denser, which one is less dense. So actually maybe you can try this. Okay, question 7, it shows the words seen through a lens. 7.2 shows the same words without the lens. Okay, so you find that it is actually magnified, right? And it is also upright. It is the same orientation as this. So what are the two properties? It is virtual because it cannot be projected on a screen. So if it's upright, it definitely is virtual, UV, like your ultraviolet. If it's inverted, then it must be real. Okay, so this is your IR. Okay, sketch the ray diagram to show how the image in figure 7.1 is formed by the lens. Okay, so this sketching of the lens, what do they give us? They give us the object. Did they tell us anything? Never, right? So it's free play, but you have to have the image on the same side, because if the image is on the same side as the object, then it will be upright and virtual. If the image is found on the other side, traditionally O-level, object is always placed on the left hand side. So if the image is found on the same side as the object, it is upright and virtual, UV. If the image is found on the opposite side of the object, with the lens as the reference, then this image is going to be inverted and real. So we have 3 light rays that can help us. The first one is this. Okay, it's parallel to principal axis, and after that it will cut F. Okay, so actually doesn't matter. For this question they give you free play. So which one do you want to set first? Maybe if you want to set your image, okay, you set your image. Okay, it must be upright, it must be virtual, so it is dotted, and it must be magnified. So you measure the length of this object, and as long as your image is larger than the object height, yeah, okay. Okay, so we know that we have one light ray that is parallel to the principal axis. Then yeah, so after that you will also have one so parallel to principal axis, and then it will cut F. So this is the part where it will cut, but how do I know it cuts there? That means your dotted line over here, okay, must be at this point, right? Because all this part is actually dotted virtual. Okay, virtual. So with that, you fix your F. Okay, and after that, you will also have one light ray that passes through the center of the lens. Okay, and again, because this image is virtual, you draw backwards. Where they meet will be the position of the image. Okay, now it is very important for you to do your own drawing when you're doing your revision for ray diagram. For drawing for lens diagram, because when we presented to you the final answer, it seems like quite easy, but you actually have to try to do it. So when will this happen? It happens, this is actually case number 6, the last case, case 6, when the object is between center of the lens and focal point F. Okay, when it's in between. Okay, there are actually 6 cases. So maybe for your revision, go and replicate all these 6 cases. Okay. Now, question 8.1, it shows two parallel plates connected to a high potential difference. A small uncharged metal ball is positioned in the middle. Okay, so this is high potential difference. So we don't know where's positive and negative, right? But doesn't matter. They want us to draw. Oh, they told us left plate is positively charged, right plate is negatively charged. So if you are connected to the positive terminal, you will be positively charged. So this is the answer. Take note, there must be equal number of negative charges on left hand side and equal on right hand side. Induced in the ball, okay? That means I need to draw on the ball itself. Because here is positive, right? Here is negative. So electrons will be attracted to this side, okay? Attracted to the left hand side. Then on the right hand side, the protons are remaining. They are left behind. Okay, so again, you cannot say that protons are attracted to the negative plates, cannot say, or you cannot say protons are repelled by the positive plates, cannot. It's always the electrons that are moving. Okay, so explain how these charges are induced in the ball. Now read this, electrons of the ball are drawn to the left hand side due to attraction by the positive charges on the left plate, or it is actually also repelled by the negative charges on the right plate. And therefore, it leaves the right side having less electrons and protons, thus becoming positively charged. There's an electric field in the space between the two plates. State what is meant by electric field. So this is the answer. Okay. Figure 8.2, draw the electric field pattern between the two plates. So this is what we have done in our tutorial. So 1 mark for the correct direction. So it's always coming out from positive and entering negative. And then the field pattern, right? Take note that the field lines cannot touch or cut each other. Cannot cut or touch, okay, each other. Now the ball in figure 8.1 is pulled across so that it now touches. Okay, before that it was actually neutral, right? Okay, although there's separation of charge. So now it touches the left positive plates. So when it touches, it will become positive because the electrons in the ball, in the metal ball, will be going down into the terminal, right? It will be leaving the ball, entering the positive charge. So leaving behind more positive than negative charges, so it will become net positive. Okay, so upon release, the ball continues to bounce between the two plates. So when it touches the left positive plate, right, it becomes positive. And since light charges repel, it will then be repelled to the other side. Okay, and at the same time, if it becomes net positive, right, it is being repelled, but also at the same time it will be attracted by the negative plate. Okay, so there are actually two forces. One is repulsion, one is attraction. Okay, so this force will cause it to actually touch the negative plates, and the cycle will then repeat, right? Because once it touches the negative plates, electrons will go in to this metal ball, making it net negative, and then the cycle continues. So figure 8.3 shows the graph of V of the ball with time t from the time the ball leaves the left plate until it returns. So this is our VT graph. What is important is the gradient represents acceleration. Why are we talking about acceleration? Because there is now a force of attraction and force of repulsion, right? So if the force is constant, right? If the force is constant, then I will have a constant. If I have constant force, F net equals to ma. If my F net is constant, I will have a constant acceleration. And if I have acceleration, that means I'm going to have a constant gradient in my VT graph, right? I hope you still remember your VT graph. In terms of charges, explain what happens to the ball when it touches the left plate. When the ball touches the left plate, some electrons are transferred to the plate, causing the ball to be net positive charge. And hence, explain the shape of the VT graph. Ignore the weight of the ball. Now, when the ball becomes positively charged, right, it touches the net positive plate, right? There will be a force acting on it, causing it to accelerate constantly to the right plate. So upon hitting the right plate, the ball will gain electrons and become net negative. And electric force in the opposite direction will now act on the negatively charged ball, So it will cause it to accelerate constantly towards the left plate. As you can see, there is a change in direction. The change in direction happens here. Change in direction. Okay? And there will also be a net acceleration. There will be an acceleration, constant one, in the opposite direction, in the negative direction. You see that this is negative gradient. This is positive gradient, right? Okay, state what's meant by electromotive force. This is the definition, is correct. Now, a uniform resistance wire 1.0 meter long and a component X are connected in series with a battery of EMF 12 as shown. So draw an arrow to indicate the direction of the conventional current I, okay, in the resistance wire. Label the arrow I. So you need to label, you need to show the correct direction. We know that current flows out from the positive terminal, which is the longer one. So it will flow through X, come to here, and this is the correct direction. Please remember to label it I. Now, resistivity is 1.1 times 10 to the power of minus 6 ohm meter. Determine if the diameter is 0.1. So this one is quite brutal lah. You have to apply the formula. R equals to rho L over A. Because there is only one situation, right? Do you know the length? The length is 1 meter. Okay? But diameter is 0.10 mm. So this is a trick here. Look at the resistivity. It is ohm meter. So basically your 0.10 mm is not in the same kind of units as the length and also resistivity. Therefore, you have to change your diameter to meters. Okay? So 0.10 mm, I hope you know how to change. From prefix to no prefix, you have to multiply by the value of prefix. That means if it's 1 mm to meters, okay, from prefix of milli, which is 10 to the power minus 3, to no prefix, right, you have to multiply by value of prefix. Okay, so you get 0.10 divided by 2 because the area is pi r square. Okay, so you should get 140 ohm. Now, suggest a replacement for the resistance wire in figure 9.1 so that potential difference across the component X can be varied. So we can use a rheostat or potential meter. So maybe you are not so sure about potential meter now, but it's okay. So we can just talk about rheostat. Now, figure 9.2 shows how the current in component X, this one, okay, depends on the potential difference V across it. So this is an IV graph, and we see that it is not a constant ratio. Okay, for ohmic conductor, IV ratio is a constant ratio, it's a straight line, but over here is a curve. So IV ratio, the IV ratio actually represents 1 over resistance. So you find that the IV ratio, right, actually it goes from gentle to steep, less to more. So the IV ratio increases. Okay, IV ratio increases, right? And since IV ratio represents I 1 over R, as I put IV ratio equals to 1 over R. If my IV ratio increase, that means my resistance have decreased. Okay, I hope you can see from this diagram. Okay, so explain how the resistance X changes when V increases. The IV ratio increases as V increases, which means the resistance given by the VI ratio decreases. Or maybe you should stick to IV ratio lah, because IV ratio represents 1 over resistance. Okay, so calculate the resistance of component X when V equals to 3 volts. This one's simple. You just go to 3 volts, find the corresponding current, and you apply V equals IR, you should get this value. Okay. On 9.2, draw the IV characteristics graph for a metallic conductor at constant temperature, which means ohmic, that has the same resistance as component X when V equals to 3.0. So you should have a straight line cutting through the origin and intercept with the intersect. Should be intersect, with the curve at V equals 3 volts. Because they have the same resistance, right? So at that point of 3 volts, right, whereby it has the same current, So it should look something like that. So this is the answer. Okay, that's all for today's video.